Hi guys, thank you for joining us today. The talk is entitled The Quest for the Last Nine, or the Next Nine, Building Highly Available Systems and Services from the Ground Up. And it's a privilege to be here in front of you in the audience as well as the folks on the stream. This talk I'm going to be talking for a little bit, and then I'm also going to invite Valentino from Adroll, who's going to talk about how he thinks about availability at Adroll. So we're going to start by talking about a little bit of a history of databases across Amazon when it started as a little startup. But before that, let's start by talking about Swiss Army knives. Now, Swiss Army knives were invented in 1891, and they were made for the Swiss Army for a very particular reason. It was supposed to be a special purpose tool with three specific purposes: a blade, a screwdriver, and a can opener. A blade for versatile general purpose use, can opener for food, and screwdriver to be able to service the rifle. Now, contrary to popular belief, the first set of Swiss Army knives were actually made in Germany because none of the manufacturing companies in Switzerland actually had the manufacturing capacity to build enough. Now, many, many years later, we still have Swiss Army knives, and there's still been a lot of innovations across Swiss Army knives. And it turns out that Swiss Army knives, they get bigger and bigger and bigger. And one of the things that happens is if you're, they don't really scale all that well, right? I mean, you have all of these key capabilities in the Swiss Army knife, but you're not going to carry something that big necessarily in your pocket. Now, these Swiss Army knives they remind us of a very interesting piece, which is, it reminds us of a database if you start using all of its functionalities all at once. If you're not careful, you might actually cut yourself, and you might actually end up with some availability risks at once. So, fast forwarding, to the early 2000s, Amazon.com was a rapidly growing company that continuously outgrew its relational databases because of the fact that, we were growing. And what happened was we continued to benchmark these databases. We continued to buy bigger and bigger boxes because, let's be honest, like sharding the database is actually really easy, but resharding while taking live traffic is always a leap of faith. And that makes it very difficult to do it while not having any availability risk, while live traffic is coming in. If you realize that you need to buy more traffic, if you need to be able to serve more people, and the bigger boxes just can't handle it right, you've got to be able to do resharding in real time, and that becomes very difficult, and it causes availability risks. Now, back in 2006, we started out with Dynamo. We wrote a paper about it. And Dynamo V1 was basically a very simple key value store. It was eventually consistent. It had very limited querying capability. We traded the extensive querying capability that we had earlier for predictable performance. We had, it was a replicated distributed hash table, eventual consistent. So we traded consistency for availability. We traded features and querying capabilities for predictable performance. And, it actually was kind of nice, but Dynamo itself, this is V1, this is not DynamoDB. It was basically a software that everybody at Amazon, all the people who wanted to run their services would download and install and run on their own. And it had its own set of problems, right? Because now the people who are writing machine learning algorithms and recommendation algorithms also had to be distributed systems experts because they had to learn how to operate a giant database. And it was nice because it was horizontally scalable. It allowed you to actually be able to shard your data across lots and lots of nodes, commodity nodes, very easily. But now, instead of managing 3 or 4 huge boxes, our developers were all of a sudden managing hundreds of boxes because scaling was made so much easier. And it turned out that all of a sudden our developers were the new DBAs. Because why? We still had to benchmark and order new hardware anytime we had to plan for capacity, anytime we had to plan for Q4. We still had to deal with hardware failures. We still had to have pagers on. And we still had to deal with all of the intricate failures that actually occur in a large-scale distributed system. Now, NoSQL in the cloud is not necessarily the same thing as cloud NoSQL that is built for the cloud. And what that leads to is managed services. So we started thinking about, well, what can we do in this area? What can we do to improve the availability, to improve the productivity of the developers within Amazon.com, as well as some of the customers that have come through as part of AWS. And back in 2012, about almost 3 years ago, we launched DynamoDB. Now, DynamoDB itself is a fully managed NoSQL database. It has fast and predictable performance. It seamlessly scales, and has easy administration. What that means is there's no more benchmarking or hardware. There's no capacity planning. There's no business continuity risk when you have to plan for how much more capacity you need. When it comes time for your next big launch, you configure your database with respect to how many writes per second and how many reads per second you want out of your database. And behind the scenes, all that complexity of sharding the database, all that complexity of multi-AZ durability, all that complexity of multi-AZ availability is all taken care of for you on your behalf. And best of all, if you built a database, let's say you wanted to just use the free tier and build a database with 25 writes, 25 reads, and tomorrow your application becomes really popular and you have 1 million IOPS, it's okay because you just go to the console and increase the number of IOPS. And behind the scenes, all that resharding is happening on your behalf without you having to worry about migration of data and ensuring that the right bits land in the right shards, especially during that delicate period when the resharding is happening. So what we tried to do with this was to encapsulate the complexity of distributed systems. It's built with, it's the data. Anytime you get an acknowledge of a write, anytime you do a put on Dynamo, before you actually get the result back, it's already persisted on disk on at least 2 different data centers, right? And eventually it makes it to 3 different data centers, and it's persisted on SSDs. It has fast and predictable performance as well, which is key for your availability. And most importantly, because it's built from the ground up to run in 3 different AZs, it is highly available. So even in case of an AZ-wide, a data center-wide outage, these are things that not only are we able to handle, but we actively exercise as part of our testing. So in this session, I'm going to go through various lessons we learned over the long years of going and building highly available systems. And the first lesson that we learned was managed NoSQL services allowed us to encapsulate the complexity, allowed us to strengthen our availability story in an organization within Amazon that we were able to share with the rest of Amazon.com. And we were able to provide them with a single-click experience that encapsulated all of the availability and complexity for them. Now, with that in mind, I'm going to turn it over to Valentino, who's going to talk about how they think about availability at Adroll. Now, Adroll, just to give you guys a context of what Adroll is, Adroll is an advertising company that deals with about 15,000 advertisers spanning 100 countries. Okay, so Valentino is handling over 1 billion cookies every month, and he's the CTO for Adroll. And I would like to welcome him on stage so he can take you through some of the lessons that he's learned in terms of availability.
Thank you. This is following. Hello, can you hear me? Yeah. Okay, so first of all, what is as Kawaja explained, Adroll is a marketing platform that allows companies of all sizes and types to effectively run ROI positive marketing campaigns online. And this, in order to do this, in order to be able to create value out of the incredible amount of data that is out there, we need to build the systems that are capable of ingesting this amount of data and then process all of it in real time effectively. In a very basic terms, Adroll effectively is listening on the impressions of all of the exchanges in the world. And this is effectively today is about a rate of 60 billion impressions every day. So every minute, it's about 40, 50 million impressions that our machines are going to receive and are going to have to process. And the most important part of all of this is that because we are directly hosted on our customers' websites, or we are buying advertising online as people are browsing the web, if we are down for 1% of the time over a year, so 99% uptime, and we are a $100 million company, this means that effectively, Adroll is more than a $100 million company, but if we're down just 1% of the time, this means losing more than $1 million of revenue. Not only that, but there is a finite number of impressions on the web every single day, and if you are down for 1% of that day, and that happens to be the moment in which one of our customers has a sale, our customer loses revenue because we weren't able to drive all of their potential customers over to their site. And so, if this wasn't enough, and this already is enough to have a very complicated business to run at the scale that we do today, we also need to maintain 100 millisecond latency. So there's a lot of talk about real-time systems in recent years. real-time for us is in the traditional sense. There are three types of real-time systems. There are soft real-time systems, which are usually those that if you don't hit the deadline, the system continues to work, degraded state, but somewhat is fine. There are hard real-time systems, like the car ABS system, where if basically the car control system doesn't hit the deadline, it's completely shut down, and it just breaks normally. And then there are firm real-time systems, which is what real-time advertising is today. And effectively, that means that if we don't hit this 100 millisecond deadline, the result is completely useless. But if we don't hit it often enough, the entire system effectively starts to crash and burn, because all of the exchanges start to bombard us with even more requests, or they start to send us almost no requests, which means that we lose even more revenue. So all of this it's really complicated to run, especially because traffic comes from everywhere in the world. And effectively, there is not enough time for light to travel from one side of the world to the other. And the only way to do this is to leverage global presence inside AWS. This has two actually big benefits for us. Not only thanks to being everywhere in the world, if a region were to go down or there would be some kind of internet disruption in Europe, using a DNS service like Route 53, you can route traffic to another region that is available. And from the point of view, instead of our availability in different exchanges, by being able to be very close to the exchanges, we have the ability to use the maximum amount of time for our machines to process every single one of the requests. And on top of that, we can actually be located close to the specific exchange. So if a specific area in the world were to have a problem, only the exchanges that were in that region would be impacted. So having a global presence allows us to be both available at all times, but also route around the problems of the internet that don't really depend on us. And so naturally, all of this is a very complicated system. And one might think that when there are so many moving parts, that the company might want to move a little bit slower. Maybe you don't want to push right around Thanksgiving, because a lot of families are doing their shopping, and you don't want to risk breaking customer sites, or you don't want to take down your infrastructure. And so maybe you think you're gonna be a little bit more careful, maybe only put the best of the best engineers that never make any type of mistake on these machines. And if this is really what you're going to think that Adro does, or that a company in this situation should do, well, you would be wrong. Andy Jassy said this morning too, and Mark Andreessen added one of his famous tweets not too long ago, talked about how cycle time compression is probably the most underrepresented and underrated force in determining winners or losers in general. Andy Jassy today talked about speed, and that's why Amazon today released a lot of lifecycle tools. The reality is that if your company is going to slow down as the complexity is growing of your systems, then even your pace of innovation and your ability to improve your products is going to slow down. And that's the last thing you want in a market that continuously have new competitors and has a very low barrier to entry like advertising. And so how could we possibly create a fast-pacing environment in which we can release software constantly, and we don't need to be scared about holidays coming up or sales of our customers? We need to build a platform that is reliable and that we can rely on as we move forward. And every step we take, we have a guarantee that the system that we have deployed is rock solid. And we do this using Brooklyn deploys. It's a fairly common strategy of deployments. It's what Amazon Apollo that they released this morning does, what multiple other companies like Netflix do. At Adderall, it is a very tough to scale problem. Effectively, all of our machines, and there's thousands of them all around the world, report thousands of real-time metrics into our metrics dashboards. And this is the dashboard that we use, for example, to run releases. In the middle, when the graph goes down, it's because it goes about to half, because two clusters have been spawned next to each other. And using these dashboards, even in an automatic fashion, we can tell if the system is behaving correctly compared to what the previous version was doing. And once we are actually absolutely sure that there are no possible issues ongoing in the infrastructure, in the new pieces of code that we're sending out, then we roll out the new version and retire the old one. Of course, it's complicated, and sometimes the systems are way more complicated to deal with than just rolling in and out software. For example, if you're dealing with databases, it's very, or state, rolling state in and out like that with different machines, it's extremely complicated. And so we were faced with the challenge of where do we put all of the states that these machines generate. Every one of these machines is bidding on behalf of our customers for more than 30 to 40,000 campaigns every moment in time. And it's very complicated to maintain a distributed state on 30,000 objects across thousands of machines distributed around the world, and make sure that when you do a deployment and you replace an old set of machines with a new set of machines, then none of that data is getting lost. And so how did we end up going there? Well, state is a very complicated thing to deal with, and it's the last thing that I would like to figure out how to fix. And so as Amazon shifted their loads over to DynamoDB and they ended up gaining a little bit more availability, we ended up doing the same. All of the machines moved to being stateless. There's no baggage that they were carrying around as they were operating. And effectively, the infrastructure has been designed and changed so that all of the machines, instead of talking to each other or even maintaining their own state internally, they would instead communicate through the other Amazon Web Services that are available. So effectively, all of the requests come through the ELB, and the configuration for each machine is pulled from Amazon S3. But then every time these machines change any type of configuration or internal state, instead of talking to each other directly on the network, they might go down or change version or whatnot. They instead push all of their updates inside Amazon Kinesis. The stream that goes into Amazon Kinesis is a stream that does about 600,000 updates every second. And basically, they keep track. These machines are keeping track of this state, of the state of spend of 30,000 campaigns through about 600,000 objects. And these 600,000 objects are replicated from Kinesis to all of the regions in the world inside DynamoDB. And the machines themselves then update, fetching again the data from DynamoDB. All of this that might seem complicated system is in fact extremely stable. And we have noticed while running this new infrastructure that the discrepancy between the data that we were seeing in the logs at the end of the day and the data instead that we were seeing in real time was less than 1% off, and for less than 2,000 objects out of 600,000. So effectively, because of the low latency of the entire system that we ended up building thanks to the Kinesis service and the Amazon DynamoDB service, we were able to effectively remove the state from all of the machines, which then didn't need to worry about any of that anymore. They just talked to the services, and then the rest of the protocol did all the necessary steps. And so ultimately, what did this allow us to do? There's more than 500 real-time instances that are running in 4 different regions. When we do a rolling deploy, this rolling deploy takes about 45 minutes. And it takes 45 minutes because we just want to be very safe that all of the data and all of the spend information and the metrics are moving in the right direction, and they're not going to have strange spikes when more load goes to them. And it's about 1 engineer that runs through all of this process for all the 4 regions in the world. And we basically have no downtime. There is no quantifiable downtime that we see from all of their metrics, all of the exchanges that we work with. And basically, all of this stuff is automated. So the engineer is there just in case of something that needs to be rolled back, but they're not there in order to make any type of decision about when something is going to be fully rolled out to the rest of the infrastructure. And so there's companies, there's our competitors, public companies that run very similar infrastructure with perhaps their own data centers or their own databases in the back. And the matter of fact is that Adderall is not a database company. It's not a storage company. We generate more or less about a petabyte of data every month of compressed data. We're not a storage company, even though we generate that much data. And we're not a database company, even though we run about 1 million requests per second on DynamoDB. We just happen to have loads that are very similar to what a database company would need to be able to sustain if they were to write a software like DynamoDB, or a company like building something like S3 if they needed to store that much quantity of data. But we don't want to spend the time on those things, but we need to have those rock solid. And by using DynamoDB and Amazon S3 and Kinesis, we've effectively been able to defocus our attention from the things that were not adding value to our customers. Our customers don't see if we're using DynamoDB or not, but they do see when we're not up, and they do see when we overspend on their campaigns. And also, our engineering team can actually, just instead of growing just because our infrastructure is growing, can grow because we need to build more products rather than because we have more machine going around. And so this is it, basically. All right.
Thank you. So some of the tools that Valentino mentioned, just if you want to look them up, one of the things that he mentioned was Route 53. Route 53 allows you to have latency-based routing, so you can actually route your customers automatically to the closest region, but it also has built-in health checks, so you can automatically take out entire deployments when they're no longer passing these health checks. And there's a lot of tools like that that are available to you within AWS. Also things like elastic load balancers that allow you to balance your load across multiple availability zones within EC2, and then how you can stitch them together with Route 53 as well across regions. So with that said, we're going to go through some of the secret sauce for how you actually create a successful service, and what are some of the deployment practices that we employ within AWS. So within AWS, when we start thinking about how we're going to build a new service, we start by looking at the customer and what is the problem that we're trying to solve. We start by writing a PR and FAQ and so forth. And then we start going down this virtuous circle of, you start by architecting, then you develop, then you test it, then you have to deploy it, monitor it, reassess your goals, and then repeat that cycle over and over again. Now, in order for you to be able to do that, there's a lot of innovation that needs to happen. There's a lot of deployments that need to happen. You need to be continuously able to improve and enhance your system without having any downtime. So first and foremost, what you have to do is after you've done the architecture and evaluation and the coding, you have to be able to test. And testing is pretty much a lifelong journey because things will continue coming up. And some of the corner cases might start to come up, and you might start to think, well, the law of large number is your friend. Why? This is a very small scenario. It only happens 1 in a million times. But the problem is the law of large number is your friend until you actually hit large numbers. So when you're running services at the scale that, for instance, Valentino is running at, small incidents, small probability incidents are normal occurrences, right? So you have to be able to plan for success. You have to be able to plan accordingly and make sure that you have the tests in place that can detect some of these anomalies. Some of the things that we do at Amazon include using formal methods and actually doing formal proofs for large-scale distributed systems that we're changing. But more importantly, you got to basically be able to embrace failures. You got to realize that failures are going to happen, and you shouldn't be surprised. So the things that we do as we do our deployment, as we improve our software, we got to do the basic unit testing. But then you also got to do things like fault injection. What happens when different parts of the system actually start to fall apart? What happens when the system grows out of bounds and goes beyond what you imagine? So that's the scale testing part. What happens when you brown out a network? How does your system actually deal with the two data centers that are not necessarily connected in the best situation during an internet outage, for instance? What happens when an entire data center goes down? Now, Netflix, for instance, has open sourced a lot of the Chaos Monkey and Chaos Gorilla stuff that does a lot of this stuff as well. And we at Amazon, when we start deploying services, when we do incremental deployments, we do a lot of this testing to ensure that our system is resilient to some of these things that can actually happen in any large-scale environment. But after you're done with the testing, after you have validated that this process that you wrote, the pieces of software that you wrote actually are going to work, you're going to deploy this into the wild, and how do you deal with that? So first of all, when we start doing the deployments, we deploy with a lot of care, and these are things that you can involve in your service as well. So you got to pay a lot of attention to what your release cycle actually looks like. Now, within Amazon, we start by doing, in my team, we start by doing a Gamma cluster, which is basically there to simulate a real-world environment. Now, it may not be running at the full scale of the real world, but you start simulating what things might actually go wrong, known issues that you might go wrong, and you try to simulate as much of the scale as you possibly can in this environment so you can learn lessons. Now, you've done your unit testing, you've done your architectural evaluation, you've done your Gamma testing. Should you just go ahead and turn everything off and put the new one in? No. So then it comes down to phase deployment. So the way we start doing this is we start by deploying the software to one of the many boxes and see what happens. You put that box under very strict scrutiny and watch. What do the latencies look like? What do the 3.9 latencies look like on that box? is the garbage collection cycle any different on this box than the rest of the fleet? And once you've gained enough confidence that this real one box is able to operate the way you expect it to operate in real life production workloads, then you're actually confident enough to start deploying it a little more aggressively. At that point, we start deploying across an entire AZ. We start going by rack, slowly, and injecting a little bit of time in each of the deployments to ensure that, if there's anything that shows up at a particular scale, you're able to roll back very, very quickly. And then after that, once you've done an AZ, then you do multiple AZs, and then you move on to different regions with some bake time in the middle for each cycle. And what you're doing there is you're really just watching your system, the new system that you have deployed, act and perform in the real world. And the other thing that you need to have in a scenario like that is to be able to detect when something has gone wrong and immediately roll back, right? Because in the time of deployment, if there's a problem with this particular software, or if you actually misconfigure something as part of that deployment, you've got to be able to automatically roll back. And that deployment rollback has to be built in, and the way you detect when to roll back is the crucial part, which is monitoring. Even after you've done the deployment, you have to be able to continuously monitor the system. So some of the tools that we use within Amazon to do this process, we've actually released today, things like AWS Code Deploy and Code Pipelines that are going to allow folks outside, allow the AWS customers to actually be able to use and deploy AWS capabilities, internal capabilities at Amazon to deploy their own software. Now, to put things in perspective, we do about 50 million deployments a year. That's about 1.5 deployments every second across Amazon. And you have to have some of this automation built in order to be able to do this effectively and safely. But what does monitoring mean, right? So the system has been deployed, and it's been running for an hour, or it's running for a day, running for a week, but you can still have issues in your system, say a small memory leak that only manifests itself after the system has been running for over a week, or it only manifests itself under a particular customer workload. To do that, you've got to be able to keep a strong eye on actually every single component of the system, and you've got to not just be worried about the average. You've got to look at the TP99. And this is not just for your performance, but also for monitoring, because TP99 is actually a great leading indicator of when things are about to go wrong. If your TP99 is consistently solid at one point, and all of a sudden it starts to slowly creep up, something might be about to go wrong. You might want to take a quick look at what's actually happening in the system. Could be a memory leak, could be a network brownout coming your way. And in order to deal with that, one of the things that we end up doing internally especially is you define a quantifiable internal SLA. And you want to set up alarms so that you can alarm whenever that SLA is breached. You want to have that baked into your alarming system, into your monitoring system. So whenever your TP99 latencies, for instance, in DynamoDB, whenever the TP99 latencies, if they ever start to exceed a particular threshold, we alarm and we start looking at what's actually happening. Is it because of an internet outage, or is it a network data center connectivity issue? But more importantly than that, so now you can actually go overboard on this, right? So one of the things you might start doing is you might set up an alarm on every little thing. And now what happens is your engineers are going to start getting pages every 10 minutes, right, or every hour. And when you start over-alarming, what happens is people just ignore the alarms, right? So you got to be very thoughtful on what alarms you set. So you got to make sure that you don't under-alarm, but you also want to make sure that you're not getting so many pages that the most crucial alarm is just going to get overlooked and get lost in the noise across all of the other alarming that is happening. And then another key lesson that we learned was don't just rely on the monitoring system that you've built yourself. So you might have a lot of metrics that are being emitted from your system, but you don't want to just rely on those metrics, because what happens if the metrics themselves are not performing well? What happens if a new deployment that you made actually turns off the metrics, for instance? And the way you validate that, one of the key tricks that you can use is you can keep your monitoring honest with the use of canaries, right? You can call them canaries, you can call them customer experience alarms, but essentially what something like this for DynamoDB would look like is create a table every minute, drop it, or create a table, insert a bunch of data, query it, and then drop it. Or have a particular table where you're just running data across, you're just running known queries over and over and over again. This means that even if your monitoring system had an issue, this third-party canary will actually detect if something might have gone wrong. And it will enable your developers to pinpoint exactly what's happening. And then it will allow you to react to any issues that might happen before your customers do, right? So it allows you to be upfront and be able to address issues before they actually become issues. So last but not least, as you start thinking about availability, the other key part of availability is the durability aspect of your system. You've got to think very diligently about the durability of the system that you're putting out there. And the key lesson here is you don't just want to think about physical durability. You can be setting all your data in the traditional enterprise. You can be sending all of your data back onto tape, and you think, everything is good because I've got physical durability. But the thing that you have to worry about is also logical durability, right? Even just because if you've built a large-scale distributed system and you've got three-party, 3-copy replicas, and everything is being replicated across 3 AZs, that's great. But you also want to be able to protect yourself against logical corruptions. What happens if somebody just comes in and drops your table? What happens if you do a bad deployment that is basically writes faulty data into your database, right? How do you roll that back? And that's the kind of logical corruption issues that you want to be thinking about up front as you design your applications is, so I've got physical durability, but what happens when I have a bad deployment, and how do I actually roll that back? Now, some of the things that help with that are snapshots, so you can actually roll back to a particular point, like a snapshot. So if you're taking daily snapshots, you can roll back to that particular point in time. But then you still have that granularity. What are you going to do about what happens if the outage or the logical corruption occurs at hour number 23? How do you deal with that? So I'll get to that one in just one second. But the other thing is, your backups are actually not very useful until you exercise them, until you restore the backups, right? So you can have a backup of all your data, but until you restore the data, you don't actually know if something is working. And this doesn't just mean that, okay, I'm going to take my tape backup and deploy it back into the system. Okay, the hard drive looks good. It means actually running the entire application back from the restored data. It means analyzing what it takes to actually do a restore when there is a logical corruption or an issue that happens in real time, because you don't want to be learning these lessons while you're going through an outage. You want to be actually able to have exercised these restorations and getting the application back up and running with the restored data over and over again. You want to do this routinely. If the last time you did the restore on your backup was over a year ago, was over a month ago, I would highly recommend reconsidering how you're doing your backups and restores and just doing a drill and just seeing what the restoration strategy looks like. So as we start thinking about restoration, one of the fundamental friends that we have in this business is logs. Logs are incredibly powerful, especially in the world of databases, because if you can get a transactional log around your database, around your storage system, you can reconstruct a lot of your data, even in case of a major corruption. And one of the things that we have built recently, and we released it on Monday, was DynamoDB streams, right? And DynamoDB streams are essentially a transactional log across your entire database, right, across the entire table. And what it's giving you is item-level ordering across all of the changes that a particular item is undergoing in your table. So with that, coupled with snapshotting capabilities, you can actually build continuous backup systems where you can actually start using a Kinesis-style API. You can actually subscribe to this and start logging and storing your data into S3 so that you can replay the log. If, let's say, you're taking a snapshot every 24 hours and you want to restore back to hour number 22, 50 minutes and 3 seconds, you can actually just continue to replay your logs until you hit the point where the corruption was. Or you can actually roll back, right? So if you know that all of the corruption happened in the last 15 minutes, you can just go look at the last 15 minutes, find out which records were changed, and only roll those back. So transactional logs are actually very powerful, and this is one of the main reasons why we started introducing access to these logs from DynamoDB directly to you so you can build applications of this nature for your availability story. Now, one of the other things that we built as part of this was we noticed that a lot of customers wanted to do cross-region replication. So as part of the DynamoDB Streams preview, we were also launching cross-region replication support for DynamoDB in an open source library that you can download and run. And all that library does really is a few simple things. One, it's able to bootstrap, so it can do parallel scans across your database and then get another table, basically to be a full copy of what you had originally. And then it subscribes to the update to the DynamoDB Streams and just copies all the changes that are occurring into the second table. Now, this table could be within the same region, so you could have a continuous backup of your data in the same region, or it could be in a different region, so you can be using it for performance enhancements and doing cross-region replication for latency purposes as well. But more importantly, you can actually just use the same library. You can extend it to do things like the continuous backup and restore that I talked about, to be able to replay your logs completely. With DynamoDB Streams, you're actually able to get your logs up to 24 hours ago. So like I said, if you can basically be archiving these logs, so you can go back as much in time as you want, or you can basically, if you think you have an outage in the last hour or so, an issue, you can actually just go back to just that particular hour. So thank you for coming, and there's the links here if you wanted to sign up for these. I'll be available for questions afterwards as well, and appreciate your time, and thank you, Valentino, for presenting with me. Right.